In this video, let's take a closer look at the end result for our electric field due to a finite line charge along the z-axis. So I've copied here again our figure that we've been using, as well as our final result from the previous video, our electric field expression. And so what I want to do now is let's consider a special case where we have an infinite line charge. So special case of an infinite line charge. And what we're going to see is this is going to simplify this sort of messy looking equation quite a bit. So for an infinite line charge, what we have is our B point is going to be going all the way up to z equals infinity, while our A point is going to be going to negative infinity. So our B is now at 0, 0, infinity, and our A, as we have it labeled in the figure above, is going to be 0, 0, negative infinity. And so we can think about what that's going to do to our limits of integration, and ultimately in this equation are alpha 1 and alpha 2. So for instance, if our B is moving up, then this alpha 2 angle is going all the way up here, and our alpha 2 is going to end up being negative pi half. So of course, as it gets further and further up, we're going to eventually be doing something like this, and our alpha 2 angle is going to be negative pi halves. Similarly, as our A point is going down here, that alpha 1 angle is getting larger and larger and larger, and eventually it's going to approach pi halves as that A point goes to 0, 0, negative infinity. So we can come down here and say that this corresponds to alpha 1. Sorry, let me make sure I get these in the right one. So this is our B point is for alpha 2, which is going to be negative pi halves, and our A point is alpha 1, which is going to be pi halves. So now all we need to do is just plug these in here, and what we can see is that this whole first term is going to become negative 2, and so negative 2 is including that, not including that, so this whole term is positive 2, and this term, of course, cosine of pi halves is just going to be 0. So ultimately then, for an infinite line charge along the z-axis, we have that our electric field is equal to, so let me put this on the screen here. So we have our rho L, and then we have that 2 divided by 4, so that's just going to become a 2 in the denominator. Our pi, epsilon naught, and rho are preserved there, and that's going to be in our u of rho direction. Okay, so there's our equation, again, for the infinite line charge. So a couple things to note about this. Again, we want to make sure that we're not getting this confused with the distance. This rho L in the numerator is that uniform charge density of our line charge. We do have a distance rho, and in this case it happened to be defined the same way as we defined rho in our cylindrical coordinates. However, as I alluded to in a previous video, that's not always going to be the case. For instance, if we had our finite line charge along our y-axis, our rho would not coincide with our rho definition that we had previously. So in general, keep in mind that this rho is locally defined, so not globally the way our coordinate system parameters were in previous units, but our rho is going to be locally defined, and that's going to be defined as the perpendicular distance from the line. So perpendicular distance from our line, and of course our u of rho is going to be in that direction as well. So for instance, as I've been saying, if we were to have, instead of a line charge along our z-axis, if we had a line charge along our y-axis like this, our rho distance would then be the perpendicular distance from the y-axis, and our u of rho would be in this direction here. So in this case, this rho and u of rho are locally defined. One other thing that I want to mention as well is, of course, an infinite line charge doesn't physically make sense, so why would we even want to bother with this? Well, it turns out that there's a lot of cases where we can approximate a finite line charge as an infinite line charge. So, of course, in this case, I've drawn my x, y, z relatively far away compared to the line distance. However, let's say we sort of zoom in here, and maybe I have an observation point that is really close to the line here. So in this case, we can see that that alpha 2 angle would be approximately negative pi halves, and the alpha 1 angle would be approximately pi halves. And so again, maybe for some particular application, this line distance is on the order of kilometers, and our distance from the line is on the order of meters. So there are certain situations where instead of using this more complicated equation, we can just approximate an infinite line charge. And again, it's not going to be as accurate, but it's going to be a lot easier to evaluate.